Okay, so today we are diving into something that might just change how you see the universe. Like literally change how you see it. Fractal cosmology.
Yeah, it's a bit of a mind bender, but trust me, it is so worth the journey.
Absolutely. So you know how like a single fern leaf has that same intricate pattern as the whole branch,
Hmm.
and then the whole plant has kind of a similar shape too?
Yeah.
That's a fractal. Now imagine that same concept, but on the scale of galaxies,
Yeah.
and maybe even the entire universe.
That's the core of it. That's fractal cosmology. Like the idea that the way matter is spread out in the universe, maybe even space-time itself, could have this self-similar structure, this repeating pattern, but across like a mind-boggling range of scales.
So it's like the universe has a hidden code.
Yeah.
Once you see it, you start to see it everywhere,
Yeah,
right?
exactly. Now, it's important to remember this isn't exactly mainstream cosmology yet,
Right.
but it's an area of active exploration, and it makes us consider some really, really fascinating possibilities.
And who knows, maybe it'll be the key to unlocking some of the universe's biggest mysteries, right? Speaking of pushing boundaries, one of the pioneers in this field is this physicist, Luciano Pietranero. Back in the late 1980s, he actually tried to map out the distribution of galaxies using this fractal idea.
And what he found was kind of remarkable. His analysis suggested that the universe might have a fractal dimension of about 2. And now I know fractal dimension sounds very technical.
Yeah, it makes my head spin a little bit, to be honest.
It's actually simpler than it sounds. Imagine like crumpling up a piece of paper. It's
Okay.
still technically two-dimensional, right?
Right.
But it takes up space so much differently than a flat sheet. Fractal dimension basically helps us quantify that complexity, that trumple factor in a way.
I like that. Crumple factor.
What Pietranero's findings suggested was that the universe wasn't just randomly scattered galaxies on this flat grid. There was clumpiness and intricacy to the way matter was spread out, and that challenged what everyone thought at the time.
Because back then, the dominant idea based on the Big Bang model was that if you zoomed out far enough, the universe would look basically the same everywhere.
Yeah.
Smooth,
Mhm.
homogeneous,
Right.
kind of like cosmic soup.
Exactly. And this is where things get really interesting. Remember the Sloan Digital Sky Survey? The SDSS?
Yeah.
This incredible project, it gave us the most detailed 3D maps of the universe we'd ever seen.
It's like giving astronomers a brand new superpower.
Right. Precisely. And initially, the data from the SDSS, seemed to support this homogeneity idea,
Okay.
at least on scales larger than about 100 megaparsecs.
So for a while, it looked like the cosmic soup theory was holding up.
It did. But here's where Pietranero's work gets even more intriguing. While that SDSS data showed things smoothing out on those really massive scales, it also hinted at a fractal dimension of 2 on smaller scales up to about 20 megaparsecs.
So it's like finding pockets of order in a larger structure that's more chaotic. Like, what's going on there? Is it possible that there are these fractal-like structures within a generally homogeneous universe? What does it all mean?
That's the million-dollar question, isn't it? And to answer it, we have to dive even deeper into the realm of theoretical cosmology.
It's like the universe is hiding all its secrets in plain sight.
Yeah.
But you're right. To crack the cosmic code, we need to put on our theoretical thinking caps here.
Yeah.
It's time to explore some of the mind-bending ideas in theoretical cosmology that might help us explain these fractal patterns.
Yeah, and trust me, some of these theories are wild. One of the most fascinating is this concept of eternal chaotic inflation, proposed by physicist Andre Linde back in 1986.
Eternal chaotic inflation. That sounds like something out of a science fiction novel. What is the basic idea behind it?
So imagine this, instead of one big bang, our universe is just one bubble in a much vaster, constantly expanding multiverse.
Hold on. A multiverse. So you're saying there might be other universes out there.
Exactly, and each of these universes could have its own unique set of physical laws, its own constants. Now, Linde's theory relies on something called a scalar field.
Okay, scalar field. I remember that term from earlier. It's like an energy landscape, right?
Right. Think of it like a constantly shifting terrain with peaks and valleys. And these peaks represent regions with enough energy to trigger rapid expansion, sort of like the Big Bang, but on a smaller scale. So each peak creates a new bubble universe. And these bubbles can even give rise to more bubbles.
So it's like those Russian nesting dolls, but with universes instead of dolls.
Yes.
Like you open one and there's another one inside and another one and another one. It just keeps going.
That's a fantastic analogy. And because this process is potentially infinite, it could lead to a fractal structure on scales we can't even begin to comprehend. Now, while Lind's theory might sound kind of out there, the idea of inflation itself is still a cornerstone of modern cosmology.
So even if, like, the details of eternal chaotic inflation aren't perfect, the idea of a rapidly expanding bubble-filled multiverse is something scientists are seriously considering.
Absolutely. It's a mind-blowing concept, but it could explain a lot about the universe we observe. Now, what's even more fascinating is that this idea of fractals, it might not just apply to the largest structures in the universe, it might also be fundamental to the smallest scales imaginable.
We were talking smaller than atoms now, smaller than subatomic particles.
Even smaller than that, we're talking about the Planck scale. That's the smallest possible unit of space and time. And some theories of quantum gravity, things like causal dynamical triangulation or CDT, suggest that even space-time itself could be fractal.
Hold on, you're saying the very fabric of reality, the stage on which the universe plays out, might be a fractal. That's incredible.
Incredible, isn't it? Now, CDT is a pretty complex theory, but the basic idea is that at that Planck scale, space-time isn't smooth and continuous like we experience it. It's made up of these tiny interconnected building blocks.
So kind of like pixels on a computer screen, but for space and time itself.
Exactly. And the way these building blocks fit together, that could give rise to a fractal structure. So at the Planck scale, space-time might actually be two-dimensional. And as we zoom out, it gradually transitions to the familiar four-dimensional space-time that we know and love.
It's like reality itself is a giant game of cosmic Tetris. That's amazing.
Right.
But how does all of this connect to the work of Alain Kahn that you mentioned earlier? His research on non-commutative geometry. It's a lot to wrap my head around.
So Kant's work is fascinating because it provides another potential avenue for fractals to kind of emerge in our understanding of the universe. In a nutshell, he's trying to find a way to unify general relativity and quantum mechanics.
Two of the biggest, most mind-boggling ideas in physics. Trying to find one single theory that explains both of them.
Exactly. And one of the key insights from Kahn's work is that at that most fundamental level, our usual notions of geometry, of smooth spaces and continuous lines might sort of break down. And guess what emerges naturally in this framework?
Don't tell me, more fractals.
You got it! Kahn believes that understanding how these fractional dimensions interact with gravity might hold the key to finally unifying those two pillars of modern physics, a theory of quantum gravity.
So fractals might be the missing link. The piece of the puzzle that helps us make sense of the universe at its grandest and most minuscule scales. That's
Right.
wow. It's mind-boggling to think that something as seemingly simple as a fractal could hold the key to unifying these massive theories.
Right.
But I have to ask, where does all this leave fractal cosmology? Like, is it just a fringe idea, or is it gaining traction in the scientific community?
Well, it's definitely an area of active research, and it's important to remember that the standard Big Bang model, especially with refinements like inflation, still holds the strongest position right now, and that's based on decades of observations, theoretical work.
Right. So it's not like we're throwing out the Big Bang altogether.
No, not at all. But fractal cosmology, it offers a really intriguing alternative perspective. It's like looking at a puzzle from a new angle. You might not have all the pieces in place yet, but sometimes shifting your viewpoint, that can reveal connections you just didn't see before.
Yeah, I like that. It's about keeping an open mind and exploring all these different avenues of thought. And even if the universe isn't a perfect fractal, the search for these patterns and this underlying order, that's what drives scientific discovery, isn't it?
Exactly. It's about constantly pushing the boundaries of what we know and asking those what if questions. And sometimes even if a theory turns out to be, you know, partially correct, maybe even completely wrong, it can still lead to these unexpected breakthroughs in other areas.
Yeah. It reminds me of that famous quote, the most exciting phrase to hear in science, the one that heralds new discoveries, is not eureka, but that's funny.
I love that one.
So even if we don't find a mini Milky Way tucked inside a grain of sand, this exploration of fractal cosmology could still have a huge impact on our understanding of the universe.
Absolutely. And it makes you think about the limitations of our current observations too, right? Like if there are these repeating patterns on scales larger than we can currently see, what does that mean? Could there be an entire unseen fractal structure beyond our current cosmic horizon? That's a question that really captures the imagination.
It really does. It's like we've only just scratched the surface of what's out there. So for all you learners out there, the next time you see a tree branching out or a snowflake forming with its intricate pattern, just remember, you might just be glimpsing the fundamental structure of the cosmos, and that is pretty pretty awe-inspiring, don't you think? Until next time, keep looking up and keep asking those big universe-bending questions.